Hi, my name is David Huxtable and I'll be presenting DP2 for Team 5 today. Our project is the Annihilator. So Team 5, just to go over some stuff from DP1, we have our mission statement, which was comprised of our customer profile and use case, customer needs and specifications. Customer profile is primary markets Virginia Tech students. Customer needs is a device that can safely crush waste and can fit in a dorm room. And specifications has to be able to have intake volume of about 1 cubic foot, apply a minimum of 90-pound force, minimum overall volume, and safe to use. That gives us our mission statement of a mini trash compactor that will allow recyclables to be taken out less often. So some potential designs for the Annihilator. We broke down 5 sub-functions into different solution fragments using the black box structure. So our 5 different sub-functions include the receive user signal, power conversion, compaction application, waste disposal, and waste intake. Each of these are made up from between 3 to 5 different solution fragments. So these include having a button or switch to start, having a DC motor, pneumatic cylinder for power conversion, some array of flat surface or ridge surface, having a chute or trapdoor to get rid of the waste, and then having an open top or some sort of rigid cover for waste intake. So from these from the accommodation table, we were able to have a functional decomposition table. Can be seen here. Each team member was able to come up with 2 separate solutions. As you can see, we've got our a key down at the bottom here to show what these or who had which solution. So if we look at mine, I had solution 5 and 6, which include having a button, the DC motor, to flat surface and piston, the swinging rigid cover for waste intake, and then a trapdoor or a chute for waste disposal. So again, each of us came up with 8 different solution fragments or 8 different solutions. This way we could go and break down from there. Another concept generation method we used was a 6-3-5 method. We got 4 different solutions from this. Due to some classmates not being in class on this given day, we weren't able to get a ton of different solutions or potential solutions from this. But one that we were able to use is shown here. So the way that the 6-3-5 method works, each team member would draw a design solution that they think could work well. It take about 2 minutes for that. And then each team member, after the 2-minute initial drawing, each team member is given another minute to add on to the solution to expand and give different ideas to everyone's different solution ideas. So Team 5, our gallery method presentation. This was a good opportunity for us to show our 8 different solution ideas that we got from the combination table. And it was also a good opportunity to get direct feedback from our primary market, which is VT students. The most important feedback we got was a trapdoor or chute for waste exit method. This way we can reduce the number of, or reduce any potential hazards from the user touching any waste. Here you can see the drawings of our different solutions. Again, as I talked about solution 5 earlier that I came up with, this has a button, DC motor, flat surface piston, swinging cover, and chute. You can see each person came up with 2 of their own different solution fragments. We were able to get feedback, which again talked about how important having safe waste disposal methods is. From these 8 different solution fragments, or 8 different solutions, we used different screening processes to break down into which solution might be the best to pursue going further or going forward. So you can see each different potential solutions labeled A through G at the top of the table over here. Along the y-axis, we have the different customer needs that were important that we discovered during customer interviews, such as the low cycle time for the waste compaction, having strong power intake, crush force, intake chamber volume, overall volume, ease of use, and safety. Each different solution, so A through G, each different solution was tested with each customer need and was given a score of either a -1, 0, or +1. -1 being that it would be below average at solving that specific customer need, 0 being it would be about average, and +1 being it would be above average. From this, we were able to sum all of the different results. So as you can see, for A, it had a net score of -2, showing that it was going to be below average. It shouldn't be a solution that we pursue further. But then if you see solution C had a score of 1, solution D had a score of 0, and solution 5 had a score of 3. These are all either average or above average solutions, so we decided to pursue these further. And this was our second screening process where we scored the best solutions. So on a scale of 1 to 5, we would rate each solution at solving the customer need. So 3 being about average, 1 being below average, or significantly below average, 5 being significantly above average. Each customer need was also given a weight. So as you can see, low cycle time was given about a 10% weight, power intake 15%, and so on. And then to get a score for each solution and the customer need, the rating and the weight were multiplied together. So the score for solution D, customer need 1, you see that 10% weight was multiplied by the rating of 3, give us a score of 0.3. These scores were then summed to give us a total score for each solution. So you can see solution D was given a total score of 3, solution C was given a total score of 3.2, and solution F was given a score of 3.75. So obviously the higher the score, the more we should consider pursuing that model or that solution. And 3.75 being the highest score for solution 5, we decided to pursue that. So here's our final design that we're going to pursue. So solution 5, you can see our non-functional prototype in these two photos here. We're going to have, as mentioned earlier, this is going to have a rigid or a flat surface compression plate. We'll be using a DC motor to power a gear, which can be seen here, and then in the CAD model, DC motor can be seen to the right. And we're going to add a gear and piston, or a rack and pinion. This will allow the gear to push the compression plate towards the waste device. This solution will satisfy all customer needs. It'll have quick cycle times. It's going to be powered through a cord that plugs into wall outlets, able to apply more than 90 pounds of force, which will be able to crush most different types of cans. And it'll have more than 1 cubic foot of internal volume, which will again allow for more waste products to be compressed at one time, or larger ones. It'll be easy to use, and it'll have ample safety features, such as a stop button, which can be seen here, and it'll have a rigid front surface or waste intake method. That way there's a barrier between the compaction device and the user. So thank you for your time, and this is David Huxtable. Thank you.